go. All right, well, welcome to CISP310. This is Assembly Language Programming. It is a class that you usually take after CISP 360. So you might want to double check that you have fulfilled the prerequisite for this class. And I am going to show you a few things. So on the screen here, this is my kind of virtual electronic whiteboard. So anything that I need to handwrite, it's going to go here. And then we have the usual Canvas screen here. And this is my view, so you may see items that you cannot see from your perspective because there are certain items that I do not think that I have hidden just because they're no longer relevant. Um, so the syllabus, okay, first thing first, the syllabus is already here. I'm TAC, by the way, in case you do not know your instructor's name, I'm TAC. I'm the instructor of this class. The syllabus is here, and also there's a syllabus video that I recorded, I think, sometime last night and distributed that also last night. So if you have not watched the video nor read the syllabus, please do so as soon as possible, okay? Because it is important to understand the expectations of how to proceed with this class. Are there any questions? The questions so far? Okay, so if you have any questions, don't hesitate to ask questions. I prefer a class that is more interactive. The worst absolute class that I have ever taught was Pascal. This is back in the good old, in I think it's in 2007, 2008 or so. Enrollment was really low, so I had three students in the entire class. And I would say three particularly not so interactive students. And whenever I talk, it's like talking to the wall. But what makes it kind of even more interesting is they usually have a little smile on their face, even though they do not respond whatsoever. So it's a strange experience. If I had three students in the class and they're just texting and using the phone the entire time, it would kind of bother me a little bit, but it's not as, shall I use the word creepy, as three people who be staring at me, smiling the entire time, but there was no interaction whatsoever. It's like, that is strange. Okay, so the reason why I put the syllabus video in here instead of talking about it in class is because I want to just shave about an hour of time so I can talk about class stuff a little bit more. Because this is going to be a very packed class, I'll give you a general map of what we are going to talk about. This is a bottom-up class. Despite what you have heard about top-down programming and top-down design and stuff like that, this is a bottom-up class. I start with a discussion of transistors, and then we'll work our way all the way up to assembly language programming in order to implement C and C++ programs. So in the end, hopefully, it will make connections to things that you already know from CISP 360. I will not be connecting to object-oriented programming, but we'll talk about control structures. We'll talk about structures, arrays, pointers, dereferencing, functions, return values, and all of those other things that you have learned in CISP 360. So at the end of this class, okay, the purpose is when you look at your C++ programs, okay, you'll get an X-ray vision all the way down to how this is done at the transistor level. So that's kind of the objective of this class, and you might probably know, can you imagine the amount of information in this class as well. All right, so moving on. So that particular role, the desktop computers will not work. Okay, so just keep that in mind. You don't need it until the lab time. Okay, so the lab is starting at noontime. So between now and the noontime, we do not need to use these computers unless you want to use it for taking notes. Alrighty, so we're gonna move on to. Are there any questions? Anything you guys want to relay to me before I get started with the physical state module? Yep, go ahead.
I don't want this to sound like rude or anything, but why is it important to learn assembly language in
That is an interesting question. I get asked that question quite a bit. So instead of me answering the question, remember, I want this class to be interactive. Does anyone want to help me answer that question? Why is assembly language programming important? Other than, oh, that's what the UCs are expecting, or that's what the CSUs are expecting. So why is that important? Does anyone want to share opinions? Okay, go ahead. We got two volunteers. Yeah.
Probably so that we can make programs that are more efficient, that have logic to them, so it doesn't mess up the internal map.
So, okay, so relating to what you just said, everything boils down to assembly language at the end. So whether you're programming in C++ or even JavaScript, okay? Now JavaScript has to go through a few layers before you get all the way down to assembly language, but it does boil down to assembly language in the end. So that is important. Let's go ahead.
I was thinking so that you understand better what's going on, like within a single line of C++ or whatever, when and there's multiple instructions, you know, you just might understand what's going on a bit better.
Exactly. That is a very good point. So the point is, everything still boils down to how memory is being utilized. Where are your variables stored? Okay, somewhere in memory. Okay, but where? How does recursion work? How many people have heard of recursion in this class? Okay, very good. So maybe that's why you're asking the question, because you may not have been exposed to recursion. That should have been discussed in CISP 360. So, if they did not talk about recursion in CISP 360, then we have a little bit of a missing piece, okay? But I will try to make up for that in this class. Because in recursion, you have a function calling itself,
Oh, yeah.
okay?
Yeah.
Okay, so you just forgot about the term maybe. So when you have a function calling itself, the local variables are local to each invocation. Wait, hold on a second here. What is an invocation? How is it different from the definition of a subroutine? Uh, The definition of a function is just describing what needs to be done, but it's just sitting there, it's just instruction. An invocation is an instance of using those instructions. So when you have a function calling itself, you can have multiple instances of the function of the computer following those instructions. And each instance can be at a different step, and they all have to maintain their own local variables as well as parameters. How can that work? It's just mind-boggling. Well, once you understand how the stack is being used, which we'll talk about in this class, in I would say week 12 or so it's going to be way in the future, then you go like, oh, so that's all that is. It's no big deal. Okay, so you'll be able to understand the some aspects of how your programs function, when we get to the end of the class. Then you go like, but why do I understand that? Okay, good question. Okay, that's because sooner or later, okay, if you write programs in C or C++, you will run into memory corruption problems. You will corrupt your stack at some point in time. When you corrupt the stack, your program would behave in ways that you cannot imagine other than, unless you take this class. You can call function f from main. When function f returns, it returns to function g, which is defined in the program, but in nowhere did you call function g. How can that possibly happen? Or it returns to a statement that are two lines down compared to the call. So if you don't understand the stack, then those problems cannot be explained, and then you won't know, oh, I need to look for memory corruption issues. What is memory corruption? Maybe I'm accessing an array past the end of the allocated space. So in this class, by the time we get to week 12, 14-ish, we'll be talking about those things. So that will give you an idea of, oh, if my C++ program is behaving in a mysterious way, what do I look for? What can possibly cause this to happen? Okay, so that's the pragmatic purpose of this class. But for the most part, from my perspective, it is just curiosity. How does a computer work? How does addition work? How does subtraction work? What is base 2? What is base 10? How are they related? So, from my perspective, when I was a student, is driven by mostly curiosity. It's like, how? Why does this work? How does it work? What is this? And so on. So I'm hoping that some of you also have the same kind of curiosity, because being joining the workforce in about 4 or 5 years, whatever we teach here is going to be obsolete by the time you graduate. Nothing you learn in college is going to be up to date. It's not the same thing in the 80s or the 90s. Okay, in the 90s, you can be graduating, and what you learn from college stays up to date for a long time, like half a decade easily. These days, things are moving so fast that most of the time, by the time you graduate, everything that you have learned is already a little bit out of date, a little bit obsolete, other than the concept that you have learned, other than the techniques, the critical thinking techniques, and how you problem solve. Those will stay with you for your entire career lifespan. So, so I hope we kind of put things in perspective. So that's a good question. Very good. Any other questions? Any other you know concerns or issues that you want to bring up before we move into the actual topic? Yep.
I noticed there was an assignment that said it was due in April, so it's missing. I'm not sure if that's just a mistake in the due date.
That's just a mistake.
Okay.
Yep. Which one is that?
I don't know what the assignment was called.
Oh, okay. I'll look for it.
Okay.
You're not supposed to see the assignments just yet. So if you see one, that means that somehow I forgot to uncheck it.
Okay.
Yep. So no need to worry about that one. The only assignment is the prerequisite checking assignment. So from your perspective, it is this one, and it is due on the 28th of August, which is next Monday by the time we start the lecture. So the prerequisite check basically is just making sure that you have met the prerequisite requirement for this class, which is haven't taken CISP 360 or a comparable class if you're coming from outside of this particular district. And I need, for those people who come from outside of this district, I need to have a copy of the petition to challenge the prerequisite by next Monday. It doesn't have to be approved. I just need it to be filed by next Monday. So, are there any questions about the prerequisite check aspect of this class? Yep.
So I filled out that the prerequisite challenge form, but then I emailed my transcript to this email address online, and they sent me a prerequisite equivalency form. Equivalency form. Which one should I fill out? It looks a little different.
I can take a look, maybe at the lab time. It should not be this one. It should be
The other one I filled out. The one.
Okay. Yeah, that would be the correct one. The one that will ask you which class are you taking, and it's which prerequisite of this class are you challenging.
Yeah.
That would be the form to file, and then you want to include a transcript from your other college or university. Yep. Okay. So you got the right thing.
Yeah.
So now for you, you just need to get into this homework assignment and upload a copy of the prerequisite challenge form to show me that it is in progress. That's all I'm asking for, is that it is in progress. All right, very good. Good thing to check with me. All right, so I got a few other links here that you do not have to read. One has to do with taking notes and maintaining notes. I have seen many people coming into my classes with nothing but a cell phone. So they'll be doing this most of the time, occasionally doing this, and frankly, I don't know how that works. Because taking notes is really important. Now, I do have to remind you that I am recording the lecture. So whatever you see here and my voice are being recorded right now. And that will be posted as soon as I can get to the recording and then push it onto YouTube, which is about a few minutes after the lecture has ended. So you have access to the recording within, I would say, 5-10 minutes, at the end of the lecture. So what do you need to do then? I mean, what are you going to write in your notes? What is the purpose of note taking? Okay, go ahead, Chris.
Go back and read your notes.
So that you can go back and read your notes. Go ahead.
To increase your understanding.
To increase your understanding, okay. So there are a few purposes to note taking. One is you can stay focused in class. Because when you're writing, when you're thinking about, okay, Tech just said something, I'm thinking this, or it reminds me of something like that, and I need to write it down, you are more focused. It's less likely that you lose your focus and go like, that champion in League of Legends is not really the best match for my tactics. Because when you're focused on taking notes, you won't have the bandwidth to think about your gaming stuff. Okay, yep. So I understand. Okay, gaming is a big part of your life, but you need to stay focused in this class when you're in this class. So the other thing is, as Chris said, it leaves behind a record of of your own thoughts when you're in this class. So it is not about what I said. It's not about the picture or the image that you see on the screen. It is about what you are thinking. Okay. Oh, this is to me. This connects to that, or to me, this picture is a better way to represent what text just said. So it is all about what you are getting out of the lecture, and I cannot record that using my own recording. It's just recording my voice and also just the screen. It does not record your thoughts, okay? What it reminds you of when I talk about those topics. So I think it is important to understand how to take notes. By this time, I think most of you know how to do that already. And this one here is a little bit kind of heavy duty. So I'm not going to talk about it. If you're curious about it, you can go ahead and click it. It is about my own process of understanding something that is quite a bit beyond my reach originally. So I'm not talking about how I understand assembly language programming because I cannot trace back the steps when I was taking CISP 360 or the equivalents of this class. So I had to pick something that is really, really a few steps ahead of what I already know. And that, in this case, was quantum computing. I had to relearn a whole new branch of math in order to just understand the vocabulary of quantum computing. So I was using that as an example to kind of look at my own process of learning something that is really new to me and go like, oh, I don't understand this symbol at all. Not that one, not that one, and not that one. So what process do I go through to dig into the content and try to understand the content? What do I do to take notes? What is in my notes? So that's more like just a reflection of what I do to learn something new. If you're interested, go ahead and read it. If you are not interested in that sort of stuff, that's perfectly okay not to read it. All right, so we're going to dig into the actual content of this class, and it is called Physical States, Truth, Numbers, and Computer. So what we'll do is we're going to go through this, kind of step by step. And remember, everything that's shown here, this is you already have access to this content. And I'm hoping that some of you had time earlier to at least take a quick glance of the material. You don't have to understand everything, but at least understanding, oh, so we're going to talk about physical states. We're going to talk about transistors. We're going to talk about how to make a gate. Okay, basically it is the hardware of an operator, a Boolean operator. So as long as you understand the general idea of what we are going to talk about, it's already helping. Okay, because it really beats someone who's coming to this class not knowing at all what we are going to talk about. So we will talk about physical states first. Okay, so physical states refer to things like, is there water here? What is the voltage over here? What is the current, electrical current over here? So those are things that we can measure using various kinds of instruments. So in the earliest days, we have computers that are called electromechanical computers. So if you have watched the movie Imitation Games, the computer that Alan Turing was working on was a electromechanical computer. It has things that rotate, contacts, that would make physical contact, and so on. But in the end, it is a computer. Okay. So these days, okay, if you say, I want to experiment and make a electromechanical computer, or at least make a component that is electromechanical, can I still do that? Can I still do it without spending a lot of money? The answer is yes, you can still do that. They're called relays. Okay, so you find relays in automobile and many other types of machinery. All it really is a magnet and a reed that makes contact. When the magnet actuates, it pulls the reed to make a contact. And if you let go of the electricity, the magnet demagnetizes, and then the reed will bounces back either just to break the connection or connect to another connection point. Okay, so that's basically a relay. It is a mechanical device. You can actually see how it works in the inside. So electromechanical computers are extremely bulky because those components are relatively big, and it also uses a lot of energy because to energize a magnetic coil, it takes quite a bit of energy, and then it also emits a lot of heat as well. So at the end of World War II, the German Enigma encryption machines received a fourth wheel to scramble broadcast communication. So if you study war history, um, the German basically had the Enigma machines. It's an encryption device. So you type in what you want to send, and then instead of sending what you type, okay, it will give you a quote-unquote garbled or encrypted output. So you transmit the encrypted output from the Enigma machine. The transmission itself is a broadcast. In other words, everybody in your vicinity, which is the entire Europe, can receive that transmission. They can see, oh, this is a character A, that's a character B, and so on and so forth. But it's already encrypted. So to anyone other than the person with a decryption mechanism, the message is useless. Yes, you received the entire message, but what does it say? I have no idea. It's just a mumbo jumbo collection of letters and characters. Okay, but if you have a decryptor, okay, which is also just an Enigma machine, it will undo the encryption, and then the plain text will be available again. Okay, so in a war, you can kind of understand how important it is to break the encryption of your enemy, because then oh, they're going to go over there. Oh, they're running out of something. Okay, and so on. So the British people, okay, the British intelligence built this machine to automatically decrypt German messages. And they were very successful. You have to watch the movie to understand it is so successful that sometimes they have to sacrifice people just so that the other side cannot know that the encryption is already broken. Okay, so watch that movie. It has a lot of interesting aspect to. Oh, now that we can decipher everything, that means we can save everybody, right? No, actually, no, because they actually have to sacrifice people to continue the pretense that we still don't know what you guys are transmitting. Anyway, bottom line, they are slow. Okay, these are very slow mechanisms. It beats having a person to do the same thing, but they're relatively slow compared to the other types of computers. Vacuum tubes is the next one. So we are just going to go through these, just superficially talk about these things. So a vacuum tube looks like a light bulb. Okay, it looks like a very small but kind of complicated light bulb. Has a lot of stuff inside. So the bottom line is it is a non-mechanical device. So that means the switching speed is faster. Okay, it's faster to turn it on, faster to turn it off. But it still takes a lot of space because the tube itself is relatively big, and then two, you cannot pack it too densely either because they emit a lot of heat. Each one is like a small tiny light bulb. You can see the glowing because that's what enables the electrons to be able to get out of the cathode of the vacuum tube. So as a result, they are much better compared to mechanical computers, but they're still pretty big, and they also consume a lot of power. They generate a lot of heat. So it's a good step forward, but it's not ideal either. I'm not going to talk about the mechanism of a vacuum tube. For those of you who are curious, you can click on these links, okay? Because these links will actually link to what a vacuum tube is, and specifically what is a triode in this case. So fast forwarding, we are going to transistors. So transistors are, they started to use transistors in computers in the 50s. Okay, that's when they first started to use transistors in the 50s. And guess what? We are still using transistors today. So in other words, as a device, as a type of device, transistors have spanned what, 70, 80 years in terms of the history of computers. So what is so special about transistors? Well, how big is one vacuum tube? Okay, just give me an idea. Okay, just a scale. Well, a little bit smaller. They're about yay tall. They are. Um, Let me see if I can find something. Oh, I know what I can use. The smallest one is about that size. Okay, because they still use vacuum tubes in certain types of amplifiers. Audiophiles, are still going after vacuum tubes, because they have a different type of tone, when they are used instead of transistors. But that's one single transistor. What is the size of a processor in your computer? What is the size of the die inside the processor chip itself? About the same cross section, right? It's just the cross section area. Then you go like, so we haven't really moved anywhere in history because the vacuum tube is about this size and then the processor is about the same size too. No, because a processor these days have how many transistors? Hmm? I think I don't think it's in single millions anymore. Okay, so let's think about this. Okay, I know some of you buy computers and you keep yourself up to date with the latest tech, right? So what is the transistor size today? If you are to go buy the latest and greatest iPad, what is the transistor size of the processor inside that iPad? I'm gonna guess. Okay, 4 nanometers, thereabout. Okay, 4 nanometers. What does it mean? 4 nanometers. What is a nano? Hmm? A billionth, right? So a thousandth is a milli, a millionth is a micro, and then a billionth is a nano. So that means, you know, a transistor is about four has a width of four of a billionth of a meter. So now I do this often, because I want to look this up too. Okay, so number of transistors in a processor. Okay, I know it's very general, but it gives you a pretty good idea. So, and I'm not sure which processor is up to date. A 486, come on, that's like ancient. So we'll take a look at transistor count from Wikipedia. And so we'll go back to 2020, number of MOSFET in trillions. 2.6 trillions. We are not even in the billion range. A trillion, 2 point something trillion of transistors on a die. So the die is basically the actual silicon, the part that actually do all the work inside the processor. And that has a cross-section area that is a little bit more than the cross-section area of this marker. And there are trillions of processors. Yes.
What does MOSFET stand for?
Aha, that's a good question. So a MOSFET, okay, so let me see if I can remember what a MOSFET stands for. A MOSFET stands for metal oxide, and then I cannot remember. The S is semiconductor field effect transistor.
I see.
Yeah, so if you are going into electrical engineering or computer engineering, you would actually have to understand how a MOSFET works. But for the rest of us, we just say, oh, it's a switch. Okay? There's a way to flip the switch on, there's a way to flip the switch off, and we'll just focus on the logic of flipping the switch and not so much how does it work? What is a PN junction? What is a P? What is the N? How does the barrier work? And so on and so forth. we're not going to dig into that. Do we have any questions at this point? Because we have gone through just a really quick history of how devices got smaller and smaller over time, but we are going to settle on transistors, and then we'll focus on transistors at this point. But do we have any questions? You don't have any questions? All right, very good. So just remember, if you do have any questions, just let me know, and I'll be more than happy to answer those questions or have a discussion, even better. So what I'll do is I am going to introduce the transistors that we'll be using in today's lab. Okay, so this is actually something that you'll be doing. So I will show you how I get this started. There are instructions in the lab already as well, so don't worry if you cannot follow these steps. And besides, I'm using Linux, and most of you are probably not using Linux on your own computer, and all of these computers are Windows, but the instructions are kind of similar, if not exactly the same. So I'll just go ahead and start up a program called Logisim. The way I do it here, don't copy. It's not going to work on your computer. So I'm just doing it over here. Nope, just 310 should be fine. Logisim. There we go. All right, so this is Logisim, and it is a program to simulate logic circuits. So we'll be building circuits in this class. Okay, at least for the first half of this class, we'll be building circuits. So you'll be asking, how does that connect to the second half of the class? Well, in the second half of the class, okay, we'll be using a very specific circuit. The specific circuit we'll be using is this one. This is the processor on which you'll be writing your programs. Why don't we just use the Intel processor? Why don't we just use an off-the-shelf processor? Why do we use this really kind of awkward processor? How many of you have seen those models of a V8 engine? Like it's made out of plastic, it's transparent. You get to see the pistons, going up and down, the crankshaft, turning and stuff like that. Some of you have. Okay, if you have not, you can always Google and just look for V8 model engine. Okay, what is the purpose of those engines? Can you put it in your car and make it go really fast? No. Can it even turn by itself? No. So what is the purpose of a V8 model engine? Or four-cylinder for that matter? Demonstration, okay, because it is made out of transparent plastic. Then you get to see, oh, so if I just turn the crankshaft a little bit, these pistons will move in all of these directions, and then the valves will open. This is going to open, that one's going to close, this one is in the compression cycle, that one is in the intake cycle, blah, 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 okay? So that way, you can freeze time and understand, so that is how it works, okay? One cylinder is compressing, meaning it's not actually doing any work. The other one is doing intake, the other one is doing this, and so on. And the way to control which cycle it's in is by configuring the valves. Are they both closed? Which one is open on this one? And so on. It's the same thing here. We can freeze time and understand how a processor works. Okay? So that is the connection between the first half of this class and the second half of this class. The first half is to say, this is the ALU. It performs addition and subtraction and stuff like that. How does it get done? We'll talk about it in 2 or 3 weeks. The second half of the class is, okay, now that we understand how the processor works, now that we understand how demultiplexers work, multiplexers work, how memory works, and so on, each component is explained. But how do they work together inside a processor? So that would be the starting point of the second 8 week. And then once we understand how the processor itself works, then we'll start to look into instructions, okay? Very specific things that we wanted to be able to do. How does it get it done? How do we string and sequence these things to do something even more meaningful? So we are building up, layer by layer in this class until all the way to the end. Then we'll be starting to implement C++ programs in assembly code. But the code is going to run on this little processor here. This processor only has 256 bytes of RAM. You're going to fit everything in that. That includes the code, the variables, the stack, and so on. And we cannot do something too fancy here, okay? But we can still fit Fibonacci. We can still fit the Tower of Hanoi, the solutions to those particular problems. They will still fit, surprisingly. So that's kind of the fun. I think it's fun because if it's not fun, I wouldn't do it. I would not use it as the content of this class. Now, just because it's fun for me does not necessarily mean that it's going to be fun for other people, but that's okay. All right, so we are getting into Logisim here. So I'm also teaching at the same time how to use Logisim. This is your tool tray, or I should say component tray. So on here, you can see that there are many components related to wiring and other categories. So for this demonstration, we just need stuff from the wiring here. This is power, okay? So you can also do zooming, inside Logisim. The zoom control, Logisim is a really old program. It doesn't have the intuitive thing of, oh, in order to zoom, we just, roll the wheel, okay? Doesn't quite work that way. Zoom control is at the lower left corner of the application. So if you want to zoom in, just kind of bump it up a little bit. So this symbol is representing power, which is also kind of analogous to the positive end of a battery. Okay? So what is the negative end of the battery? Well, it is called ground. So now we have just connected the two ends of a battery to this circuit here. And then what we'll do next is to take a look at transistors. So in order to put a component into your design, you just click here. It's not a drag to put it into the circuit. It is simply a click followed by another click. So one click selects what component you want to use. Another click will put an instance of that component into the circuit. Is that okay? All right. So I'm just going to put this over here. And as soon as you have a component selected, you would also see the properties related to the component. So when you see the properties in the selection, that means these things can be changed. So that means the type is currently a p-type, but if you click on the drop-down box, it will show that, oh, you get to choose, okay? You want it to be a p-type or an n-type. I'll explain that later. Phasing only has to do with the direction. You can rotate the component. So east means this is referring to the component pointing that way. So if you want to rotate 180 degrees, then you just have to say, I want it to face west. So that will give it a 180 degree rotation. Gate location means do you want this terminal to be on this side or on the other side? It's a mirror effect. Okay, so if you just want to flip it using the mirror effect, then you use this option. So you flip it onto the other side. Data bits for now is always just going to be 1. Okay, so we'll talk about this later when we have a splitter. All right, so this is a component. It has 3 pins. It has 3 connection points. So now the question is, here's one connection point, here's another connection point, and here's the last connection point. The question is, what are those connection points? How does something like this behave? Now, I will explain that also, but I will point out a resource just in case you need to refer to an explanation that is not me talking about it. So what you do is you go to Help, then you go to Library Reference, and then, okay, I'm going to bring the window up here. And you can see that the wiring library is about the same as what you saw earlier, and it has the same order. See, the splitter is the first one, the pin is the second one, a probe is the third one, and so on. So we go to transistor here, and now we have a full explanation of what a transistor is and what it does. So are there any questions about how to get to the reference material that is built in to Logisim? So once you quote-unquote install Logisim, you will have access to the entire reference already. So basically the built-in help is already here. This is not relying on the internet either. You can do all of this once you have the program installed. You can use it anytime you want. You don't need internet access. All right, so shall we move on, or are there any questions at this point? No questions? Okay. So if there are no questions, we'll focus on this circuit here. The power is really, you can think of this as an infinite resource that says 1. Okay? And then the ground, what do you think? If that is 1, what do you think the ground is? It's an infinite source of 0. That is correct. Okay, so are we good so far? Power is 1, ground is 0. Okay. So once we refer to voltage as ones and zeros, then we can describe a transistor using a truth table. So let me switch to my tablet here. Okay. So we'll talk about a P transistor first. So, there we go. A P transistor. So a P transistor looks like this, okay, like that. And there's this. There's a bubble here. It's important to remember there's a bubble. And it also has a direction. Okay, so typically it has a direction. And for this example, I'll just say the direction is like this. Okay, so that is a typical symbol of a P transistor in Logisim. So now the question is, what are the 3 terminals? This is a terminal. This is a terminal. This is a terminal. Simply means that you can make connections to those particular points. This terminal has a symbol of S. This one has a symbol of D. This one has a symbol of G. This is the source. Okay, so S is an abbreviation of source. D is the abbreviation of drain. And then G is the abbreviation of gate. Are we good so far with the 3 terminals? So the flow, this is the flow direction. We always want the flow to go from source to drain, and hence the name of those 2 terminals. The flow is always from source to drain, and guess what the gate is doing? That's a switch, okay? So when the switch is at a certain state, then you are allowing flow from source to drain. If the gate is in the opposite state, then you're turning off the device and you do not allow the flow from source to drain. Are we doing okay so far with that? Okay. So now I just need to draw a diagram. And this is going to be a very simplified version of the behavior of a p-channel transistor. So we have gate here. And gate, it can either be a 0 or 1. Are we doing okay? It's a truth table. How many people know the concept of a truth table? Okay, so the rest of the class, I'll go ahead and explain what is a truth table. So in a truth table, we are looking at what does it mean when something is true and when something is false. Now, when you look at Boolean stuff, which is true, false, you can always just think of true as 1, and you can always think of false as 0. Okay, so that's why in this class, you will not see me using true or false most of the time, and instead I would use 0 to represent false, and then 1 to represent true. Is that okay? All right, cool. And then in the other column, I will simply say, are we allowing flow from the source to the drain? Now, for this one, when the gate is a 0, we are allowing flow. And when the gate is a 1, we are not allowing flow. In other words, if you want to turn on the switch, gate should be 0. If you want to flip the gate, if you want to flip the switch off, then gate should be a 1. Are we doing okay so far with this? Okay. So now we look at the companion, which is an N-type transistor. So this is an N transistor. And it looks almost the same, except it doesn't have a bubble. So it has the 3 connection dots here, has a flow, source flows to drain, and we have a gate. And then the truth table is, for the most part, the same, except things are just a little bit opposite. The gate can be a 0 or 1. When the gate is a 0, we are disallowing flow. When the gate is a 1, then we are allowing flow. Are we doing okay so far with the picture so far? So the N transistor versus the P transistor, the only real difference from the perspective of how to turn it on and how to turn it off is the polarity of the gate is opposite. In order to turn on the P transistor, the gate has to be a 0. In order to turn on an N transistor, the gate has to be a 1 instead. Are we good so far? All right. So there's one more restriction of how you use transistors. So for p-type transistor, the source should be a positive thing. And then for n-type transistor, the source should be a negative thing. So in the terms that we have talked about here, this should be closer to the power, and this should be closer to the ground. Are we good so far? Okay, so that's basically everything that you need to understand from a logic perspective of transistors. Now, are transistors really just that simple? The answer is no. They are actually very complicated devices, and it will take a 3-unit upper division class at UC Davis to explain, how it works, okay, how the device works. So we are oversimplifying this entire thing to just, oh, it's just a switch. This is how we turn it on, and this is how we turn it off. Okay? So now, understanding this, we start to build a circuit. Okay, so I'll go ahead and build a circuit. And I need the P transistor to flip down. So I need it to face south, like so. And if you already have a component, it's configured the way you want it, and you just want another one of these things, you can duplicate. In fact, you can select a bunch of stuff and say, I want a copy of everything here. You can always just duplicate. So whatever you have selected here, you go to edit and then you click on duplicate, which is also Control D. It will make a copy of whatever you have. It will have exactly the same properties. So this is a P type. It faces south. It also has the bottom right configured exactly the same way as the one that we copied from, except with this one, just for looking right, I want it to go the other way. Okay, so there are 2 P transistors like this, and to drag it, you can just kind of move it. It's just to make it look nicer. The placement of the components is not significant at all in a circuit. It's just how it is connected. There we go. And now I need 2 N-type transistors. So what I can also do in this case is to say, well, since I got 2 transistors already, we'll make a copy of these 2 transistors, Control D on the keyboard. Now I have 2 more P-type transistors. Except remember what I said, I don't want P-type transistors, I want 2 N-type transistors. Okay, so how do we do that? Well, click on each one and change the type. Yes, I could have done that. But you can see that both of them are p-type, both of them are facing south, and both of them have a data bit of 1. So that means I can change those attributes at the same time for both of them because they are already the same, so I can make changes that are also synchronized. So now I can say, now I don't want p-types, I want n-types. Aha, you can see how the bubbles are now gone, so meaning they are now the n-type transistors. I need to rotate them, to go the other way around. In other words, I need the source to be closer to the ground, so I need to change the facing so that it is now facing north, like so. Okay, and I think the rest I can just it's just a placement issue. So I'm gonna put the placement one over here, and then put the other one over here. All right, so now I have all the components, well, almost all the components that I need, because this whole thing needs an input of some kind and an output of some kind. So for now, I am just going to use a two single bit input pins, and one single bit output pin over here. So what is an input pin? An input pin is like a parameter to a function. I'm giving you these information to process, okay? So it's basically the input to the circuit itself. Each one of these can only be a 1 or a 0, so they are Boolean input bits. The output is exactly the opposite. It is the return value of your function. That's the output of the circuit. Are we doing okay so far with those concepts? Input pins are parameters, and then the output pin, in this case, the single output pin, is the return value. All right, so I got everything already. So in order to make connections, you have to be careful because you can make connections to points that are not actual connections. Like this one is not a connection because the connecting point of a transistor is not here and it is over here. So make sure that you know where the connection points are. So how do you know where the connections points are? You just hover. If you hover over a particular part and the circle appears, it means it is a connection point. If you hover over something and nothing appears, it is not a connection point. And every circuit, every component has very specific points where you can make connections to, so you have to pay attention to that. Because otherwise, you can have a circuit that seems to be connecting, but is not actually connecting the way you think it should be connecting. So we'll go ahead and make this circuit here. And you can probably see there's a little big dot here. So the big dot basically means, yes, these 3 wires are all connected. So without the dot, it means they're not connected. And I will show you an example of those later. So this connects here, this connects here, and then this connects here. The output pin goes here, and then the input pin goes here, and also goes here. And then this one has to go over to the other side. So this is where we have a crossover, okay? So I intentionally make this a crossover so that I can show you the different types of junctions. Okay, so I'm going to pause right here. Do you see there's no big dot over here? See there's a dot over here, but there's no dot over here. So that means these 2 wires, okay, let me use a mouse pointer so it's actually recorded. So what this means is this wire is actually not connected to this wire. One is quote unquote flying over the other one. This is really important because if I want these 2 to actually to be connecting, there's a way to do it too. Because if you want those 2 to be connected, all I have to do is to make a stop here first, then continue drawing that wire. So now we have an actual junction. In other words, this wire versus this wire, they are now connected, which is not what I want. So Control Z is still going to undo like most applications. So I do want it to fly over because I just need this wire to go to the other side so that I can connect this end to the gate of this P transistor and connect this end to the gate of this N transistor over here. Are we doing okay so far? Any questions about the process of making this particular circuit? Yep.
So when we were connecting everything, there was some red and gray and stuff.
So I wouldn't be too concerned, when you are still building the circuit and you see those red and greens, it's not going to be a big concern. It's after you build everything, if I still see a red, then we have a problem. But that's a good question. So to read the colors in Logisim, dark green is a 0, light green is a 1, and then blue is what we call floating, which means it is neither a 1 nor a 0. It is simply not specified. We don't know what it is. Is that okay? So that was a terrific question. Thank you. All right. So we look at this circuit here and go like, but what does it do? I mean, this is a circuit here. What does it do? So what we'll do here is to basically run this circuit through logic here. Okay, so what we'll do, is I'm going to stop simulation because I don't want you to look at the zeros and ones that are already here. So we'll disable simulation. So if you go to the simulate menu, you just have to deselect this checkbox here, and the circuit is no longer running. And once I reset it, you just see blue wires here. Okay. So this gives us an opportunity to look at this and go like, okay, but what is happening here? If I have 0 and 0 as the input pins, how are the transistors configured, and how is that going to affect the output pin? That's the question I want to answer. Okay. So I'm just thinking about how to present this, and I think I can do something like this. Maybe not. I have to run through all my windows here. I'm trying to fit both on screen at the same time. Hmm. All right. Well, we can look. We can look at each one, one by one, and we'll name these transistors so it's easier to refer to them. And there's no way to name those things. That's okay. We'll just go ahead and give them names here. It's traditional to use Q as a prefix when we are referring to transistors. I don't know why. That's one of those things where I really do not know why. Is why do we use Q to designate transistors on the circuit? All right, so now we have Q1, Q2, Q3, and Q4. So can someone tell me whether Q1 is turned on or not, based on what we saw earlier? So how do we determine whether Q1 as a switch is on or off? The first thing is, what is the type of the transistor? So what do you think? Is it a P-type transistor or is it an N-type transistor? It's a P-type transistor because it has a little bubble at the gate. Okay, so that is something that we have to recognize first. So the next thing is, okay, so it's a P-type transistor, and the gate, which is the part that controls whether the switch is on or off, is a 0. Because how do we know? Because we can see that the gate is connecting to an input pin that is of the state 0. So do you recall whether the transistor is on or off? Let me switch back to what we saw earlier. Is it on or off? It is on. Very good. And the same thing applies to Q2, because Q2 is also a P-type transistor, and the gate is connecting to another input pin, but the other input pin is also a 0. So that means Q1 and Q2 are both on. Okay? What about Q3? Q3 is a N-type transistor, and the gate is 0. So is it off? It is off. Same thing with Q4, it is off as well. So what that means is if you look at things from the perspective of the output pin, which is this one here, you look at this wire, and it can split to two ways over here. Okay, it goes in both directions at the same time. But if it goes in this direction, it encounters Q3, which is off. A switch that is off is disconnecting the circuit. So that means I don't even need to look at Q4, because if Q3 is off already, there can be no connection to ground whatsoever. Does that make sense? Because you have two switches that are in series, and if you have two switches that are in series, they need to be both on in order for that segment of the connection to be on. Okay, so we can forget about ground. What about if I follow in the opposite direction? Well, if I follow in the opposite direction, it goes into here, and Q1 is on, so that means I find one path to 1, but Q2 is on as well, so that means I have two paths to 1. That means we do have connection to 1 from the output pin, and that's the reason why the output pin is a 1. Are we doing okay so far with this? When both input pins are zeros, the output is a 1. So I'm just going to pause here a little bit, make sure that there are no questions before we move on. If you need more time to digest it, you can also let me know. We do okay so far? Okay. So now we try something else. So I'm going to use the poking tool here. This is called the poke tool. It allows you to change the value of the input pins. So you just click on the input pin and it will change the state to something else. So what about this circuit here? What should be the output look like in this configuration? So we do exactly the same analysis, okay? So we look at Q1 first. So Q1 is off this time because it is a P transistor and the input is a 1, so it is not connecting. The switch is off. But Q2 is still on because Q2 has a gate connecting to a 0, so Q2 is still on. Q3 is on because Q3 is an N transistor and the input is a 1, so Q3 is connected this time. But Q4 is off because Q4 has the gate connected to a 0. So this time we have Q1 being off, Q2 being on, Q3 being on, and then Q4 being off. So what should the output read like? Should it be a 1 or should it be a 0? All right, so let's go through the simulation, okay? So we go to here, and then we have two ways to proceed. Now, if I look at the top connection, even though I cannot get past the Q1 because Q1 is off, Q2 is on. So I can actually get past Q2 so that this connection here will eventually connect to the power, which means it is a 1. But it doesn't mean that it's going to be a 1 because in very badly designed circuit, that may be another path to go to ground as well. It's called a crowbar, which is a bad thing to have. So we have to kind of make sure that we do not have a path to ground. So now we follow the other side of this split here. We look at Q3. Q3 is on because it is an N transistor and it is connecting to a 1. The gate is connected to a 1. So Q3 is on. So now we have look at this Y over here. It has to go through Q4, but Q4 is off. Q4 is off because it's an N transistor and it is connected, the gate is connected to a 0, so Q4 is off. So without Q4 cooperating, I can never reach ground, which means I find one path to the power, which is the 1, but I found no path connecting to ground, so I don't have to worry about what we call a crowbar in electrical circuits. Is that okay? So in this configuration, the output is still a 1, okay, just like the last time. So the next configuration is flipping this 1 and this 0 here. I'm not going to talk about this one because the circuit is symmetric. So this is basically the same quote-unquote same configuration, except transistors Q1, Q2 will flip their state, transistors Q3, Q4 will flip their states too. But all that is doing is to change which path we can use to go to the power and which transistor will break the connection to ground. So we still end up with just one path to 1 and no path to 0. So the output is still going to be a 1. Are we doing okay so far? All right. So now we have the last configuration, which is a 1-1. So with this configuration, both of the p-type transistors will be turned off. In other words, Q1 is off, Q2 is also off, because we have both of those being p-type transistors, and they're both having their gates connected to a 1, which means both of them are off. But at the same time, Q3, Q4 are both on as well, because Q3 and Q4 are both N transistors, and they both have the gates connected to a 1, so they're both on. So this means the output pin can find no path to the power, which is the 1, but it finds one path to the ground, because Q3, Q4 are both completing the circuit in order for the output pin to connect to ground, which is a 0. So only in this configuration, the output is going to be a 0. Do we have any questions about all of this stuff here? Yep, go ahead.
The V, or kind of quote unquote V.
Yeah.
Is that just for directional?
It is it's telling us what is the flow. So that's a very good question. Okay, so what are we flowing? So what we are flowing depends on the type of the transistor. If we're looking at a p-type transistor, we are looking at the flow of positive charge. Okay? When we're looking at an n-type transistor, we're looking at the flow of negative charge. So the ground is a gigantic infinite reservoir of negative charges. The power is the same, but for positive charges. So the direction of the transistor has to match the type of the transistor, and then you have to point it in the right direction. So that's a very good question. All right. So the circuit would not work if you have the flow, in the wrong direction. So you have to make sure that the flow is in the right direction. All right. So I am going to take roll right now. And for those of you who do not know how I take roll, I'm going to show you right away how I take roll. So what I usually do is I go to the Canvas website here, and I'll just add an activity that you can participate in. And typically I make it an assignment. You cannot see it yet here because I'm still working on it. And I want to create a new one. Oh, I need to give it a name, but where's the name? Oh, right here. There we go. So I would typically would use today's date as the name. So today is the 21st, and this is for roll taking purposes. And unfortunately, it adds it all the way to the last portion. So I'm gonna have to, oh, I've got a bunch here. I could have recycled those. So what this means is you probably want to use your mobile device to sign into your Canvas account. Like now, so that by the time I'm done with this, you can actually go in and finish the activity. All right. All right. So there's not much you have to do. The only thing you have to pay attention to is what is the passcode. But I changed. Huh. Okay. So first of all, I will make this do in 10 minutes. Okay. So we'll make it 11:50 a.m. 11:50 a.m. And there should be a place where I can specify a passcode. Oh, I think I should make a quiz instead of an assignment. Okay, never mind. My mistake. I'll just reuse one of the existing ones. All right. Move this one up. And make some changes. You cannot see it yet here, but do sign in. So you'll be ready to do this when it is ready for you. All right. All right, so the access code is just PN, lowercase. I'll write it on the whiteboard. And I will change the date. So today is August 21st. Oh, I can just use the time too. And then change the name of the activity so that it's not confusing. Today is 0821. And then for the questions, it is really easy. You just have to say, yes, I'm in class today. That's all you need to do. And click Save and Publish. So if you refresh your browser or your app, you should be able to see that so-called quiz right now. And you have until 11:50 to tell me that you're here. The passcode is once again PN, lowercase. So tell me whether you are seeing this or not and whether you can get into it or not. Okay, great, excellent. You can do this on your phone, you can do it on your computer, you can do it on the desktop computers here. Yep.
On the
Hmm?
Or PN.
Yep, just lowercase pn.
Would it still count you as president if you put false?
uh, I'm about to say something that I do not mean to, but I will take it as present also. The thing is, if you put in yes, then it automatically count as a point. So it makes it easy for me to count the number of absences. All right, so this is how I take roll, and I do not usually take roll at exactly the same time in each class, and sometimes I don't even bother to do it, but I have no idea which day I do not take roll, and which day I take roll at the beginning of the class, and which day I take roll in the middle of the class. So, but that's how I do it. All right, so getting back to what we are doing here. All right, getting back to the circuit. So what is the purpose of this thing then? I mean, if at least one input is a zero, the output is a one. If both inputs are ones, then the output is a zero. So it doesn't seem to serve any purpose whatsoever, except I can make this out of 4 transistors. So let's take a look at the truth table again. So I've switched to the tablet, and we'll take a look at a truth table. So this time I'll call the inputs x and y, and then we'll look at the output. Okay, so that means if inputs are both 0, the output is a 1. If one is a 0, the other one is a 1, the output is still a 1. If the other one is, if I flip the input states, the output is still a 1. If both are, oops, I got this wrong. If both are 1s, then the output is a 0. So are we agreeing on the summary of the behavior of that circuit using just a truth table? This time we are not even taking a look at the transistors or the connectivity. We are just recapping, okay, from the perspective of the input and the output. This seems to be what the circuit is doing, right? So you look at this. Do you recognize an operator in Boolean algebra, big Boolean logic, that can do this? It has 2 inputs, meaning you have an operator with 2 things that it operates on, and then it gives you a result. Go ahead. It's a NAND. Very good. It is a NAND starting with an N. Why is that? Well, if you think about this, okay, it is the negation of x and y. That's a NAND. So this is also known as x NAND y, negated AND. Okay, does that make sense to you? When x and y are both zeros, in fact, if at least one of x and y is a zero, the conjunction, the AND, is going to be a 0. But when you negate a 0, you get a 1, right? So that means just intuitively, we can put 1, 1, and 1 here for the first 3 rows. When x is a 0, y is a 0. When x is a 1, y is a 1. When x is 1, y is a 0. The output will all be 1s, and is consistent with the negation of the AND of x and y. Well, what if both inputs are 1s? Then x and y is a 1, but the negation of the 1 becomes a 0. So that puts a 0 here as well. So using a truth table, I have just proven that the output of the gate is indeed just x NAND y, x negated and y. You go like, wow, well, that's an operator that I have never learned in CISP360. So what is the purpose of this operator? Why is it even important? Now, without going into details, because in 5 minutes I cannot possibly cover everything that I need to talk about, this is the one operator that you need to make the other operators that you are already familiar with. What other familiar operator are we talking about? Just the usual not, okay, the exclamation point, the conjunction, which is and, which is the double ampersand, and also the or, which is the 2 vertical bars. Those are the operators that you are familiar with because that's how we use in language as well. So negation, conjunction, and disjunction are concepts that we use in languages too. But the NAND operator can be used to make all of those other ones. So I'll do a really quick run here. So x not x is the same thing as not x and x, right? I mean, x and x is really just x. So if I negate that, it becomes just not x. Does that make sense? Okay. Well, I have just used NAND to implement a simple not. Are we good so far? So the other ones are a little bit more obscure. Okay. So let's take a look at x and y. What is that supposed to look like? Well, we have x and y, but the only thing we can do is to negate it. So what if I do this? Well, this is a n, okay? This is another n, right? And yet, this is another n. In other words, I have just used three, well, technically two, but you can count it as three. So we have used multiple NAND operators to implement a regular AND that we are familiar with. The OR is a little bit, it's more tricky, okay? So we have X or Y. So if you know De Morgan's law, it is the same thing as not X and Y. Let me think about that. Nope, I take it back. So let me undo this. Okay, so let me use a Boolean algebra here. It is not the not of X or Y. Okay. Okay, so we're not quite at the answer yet, but do you guys agree that double negation cancel out? Okay, all right. So now this is the part where you guys go like, are we really sure about this? This is called the application of De Morgan's law. So De Morgan's law will take the negation of something and it quote unquote distributes the negation into the operator, but it changes the operator from and to or it changes from or to and. You have to flip between those two operators. So once I have this, it is not too difficult because now we just have to not x and x itself and not y and y itself. Okay, so now we have all NAND operators here. Why? Because we have, once again, I'm going to use my pointer here. So we have, okay, it doesn't show my pen location. So we have n and, we have n and then we have one final n and over here. You look at this and go like, isn't that going backward? Because we start with something so simple and then we end up with something that's kind of messy. Well, you can look at it that way. It does look a little messier than before. But at the same time, if I ask you, if I give you an infinite number of P and N transistors, can you make me a regular OR gate? You go like, yeah, we can do that, but it's going to be ugly because there will be a lot of transistors. But we can do it. Why? Because this is basically just three NAND gates. Okay, NAND 1, NAND 2, and then NAND 3. You just have to feed the output of one to the next one, and so on and so forth. But there's a way to build it. Are we good? What about a regular AND gate? Same thing. If all you really want is just regular AND, we can build it using NAND. But we can do NAND using 4 transistors. So that means if you just give me enough P transistors and N transistors, I can do it. Same thing with regular NOT. That's just a single NAND gate with both inputs tied to exactly the same input. Yeah, we can do it. So what is the whole purpose here? All this is showing is if I'm not optimizing for number of transistors, we know how to use transistors to implement the regular operators that we are familiar with. Not and or can all be implemented using just regular P and N transistors. That is the significance of this particular lecture is we'll talk about exactly how to build a circuit next time, but I think all of us are convinced that yeah, we can. It's just a matter of where the wires are going, but we can do it. So are we doing okay so far? All right. So we're going to have a short break, and then at noontime, I will open up the lab activity, which is going to be visible on Canvas. So when you come back, there'll be a lab activity. Now, the lab activity is not just something that you do during the lab time, and then you can forget about everything that you have done. You might want to take notes because the techniques and also the knowledge that you learn in one lab is usually applicable in a future lab. So you might want to keep notes of, oh, so this is how I do blah, blah, blah in Logisim. Just write down some notes, just so that next time you know how to do that, okay? And I will also set up exercise, practice labs too. So after the lab is due, I'll give you a lab that does not count for points, but you can do it as many times as you want. So this way you still have access to the instructions of how to do things. Okay, so I'll see you guys at noontime in the lab, and meanwhile, I'll go set up everything else. And I can stop the recording and